My name is Ho Ziwei, matrix number 147118. So now I'm going to talk about what you have to do in the LIDIS experiment. So first you have to set up the experiment like this. Then you have to add a drop of oil into each hole of the disc to increase the thermal contact between the disc and the thermometer. Then secondly, you have to start the heating by using voltage not more than 5 volt and current around 0.4 ampere. Heat until the temperature of C or B about to reach but not exceeding 40 Celsius. Then reduce the current by adjusting the rheostat until the current drops to 0.25 ampere. So at this point, you need to record the current and the voltage at this point, and these two data will be fixed throughout the experiment. Measure the temperature of A, B, C for every 1 minute interval, and you need to take at least 30 readings. Repeat the experiment by changing the value of the current to 0.3 ampere and followed by 0.25 ampere. So after you have done all the 3 experiments, you have to measure the thickness and the diameter of the disc A, B, C and perspex, and then calculate the cross-sectional area of all the discs. After that, you have to plot a graph of TA, TB, TC and TB minus TA against 1 over time and determine the temperature at steady state. So how to determine the temperature of steady state? From the graph, which is you need to look for the y-intercept of the graph. So this will be the temperature at steady state. Then you have to compare the temperature at steady state you get from the graph and you get from the table from the reading you record just now. And the temperature at steady state is required for the calculation of thermal conductivity of perspex. So you have to determine the temperature at steady state very precisely, so you can get the thermal conductivity. So how to calculate the thermal conductivity? We have a formula here as shown. So you substitute all the formula in all the values, and you can get the value of thermal conductivity of perspex and calculate the error for the value of thermal conductivity. So now I'm going to talk about what is the problems we face during the experiment. So one of the problem is the sensitivity of the thermometer, because for the thermometer the calibration is 0, the difference is 0.5 Celsius. So but as we know, the heat conductivity of the perspex is very low. So the changes in the temperature of this air is maybe really small. So if the thermometer is just 0.5 Celsius difference, there will be some changes in the temperature of this air that we could not detect. So this is one of the problems we face in the experiment. And another problem is the inconsistent temperature. So the fluctuation in the temperature of the environment will cause the sudden heat, more heat loss or sudden less heat loss to the surrounding, which is not consistent and causing our result deviate from the actual value, theoretical value. So this is random errors that we cannot avoid, but we only can minimize it by doing the experiments more and take the average value. So the last one is the condition of the disc. So sometimes the condition of the disc may be uneven, so causing the physical contact area between one disc and another disc maybe not the same. So maybe this is uneven. When it match with another one, it cannot fit perfectly. So this is one of the problems we face in the experiment, as this is not fully in contact with another disc, causing not complete heat transfer. So what I have learned from the experiment is that is the way to conduct a Liddy's method experiment. So as you know, Liddy's method is a method specialized for determining the thermal conductivity of a low conductivity material such as perspex and glass. So by doing this experiment, I know the way to measure the thermal conductivity of a low conductivity material, because if we are using the normal way to determine the thermal conductivity for the we are using the normal way to determine the thermal conductivity for a low conductivity material, the changes in the temperature may not be detected, or it may take too long time, so it's not efficient. So after these experiments, I learned how to conduct the Liddy's method experiments and how to measure the thermal conductivity for the low conductivity materials such as perspex. And yeah, as I know how to calculate the thermal conductivity using the formula and plot the graph, and know the and can link with the real life of Liddy's method, the applications in our real life. The example of good heat conductor is metals include such as copper, silver, gold, aluminum, iron, mercury. So for mercury, as you know that we use mercury in a thermometer, what is a good heat conductor? It means it can absorb heat very fast and also release heat very fast. So when we use mercury in the thermometer, so when we place the thermometer into something that we want to measure the temperature, so the mercury will immediately absorb the heat from the substance we measure and quickly expands and reach the reading of the temperature. So this is one of the application of the good heat conductor in our real life, which is mercury, and we use it in the thermometer. We place it in something that we want to measure the temperature, and it quickly absorbs the heat, good heat conductor, and quickly quickly expands and reach the reading that we want. Reach the reading of the temperature, of the object, and after we remove it, it also quickly drop to the normal temperature, which is the room temperature. So it absorb heat very fast, releases also very fast, so very convenient. And for the example of bad or poor heat conductor is wood, paper, air, cloth. So those things, they are bad in conducting heat and also bad at releasing heat. So what is the application of high thermal conductivity material in our life? So for an example, the high thermal conductivity material will be used in heat sink application. So what is heat sink? Heat sink is a passive heat exchanger that transfers the heat generated by an electronic or a mechanical device to a fluid medium, often air or a liquid coolant, which the heat will be dissipated away from the device, thereby allowing the regulations of the device temperature. So for an example, if there's a motor running, the electronic device is running and the temperature increases very fast, so the device will be very hot. So we use a high thermal conductivity material placed close to it, so the high thermal conductivity material will quickly absorb the heat from the device and also quickly release the heat to the surroundings. So this will allow the regulation of the temperature of the device, so the device will not be broken and can be functioned normally. So the high thermal conductivity material can absorb the heat from the device. So what is the application of low thermal conductivity material in our life? So the application is in the thermal insulation. So what is thermal insulation? Thermal insulation is to prevent the flow of heat from a warmer place to a colder place. Like during winter in house, we want to keep the house warm and do not let the heat flow to the outside. So what is the example? One of the example is wool, WOOL, which is a fabric textile obtained from the sheep. So this substance wool, WOOL, will have a low thermal conductivity. So when we use it in our clothes, it will prevent the heat loss from our body to the surrounding during winter. So it's a good example of thermal insulation.